Now, in this video, we're going to look at rational functions. A rational function is a ratio of two expressions. That's where the word rational comes from, because we have a ratio. We have 2x over x plus 1. You can think of it like that. This function is defined for all values, all real numbers x except x equals minus 1. You see, if we try to evaluate this function at minus 1, we get 2 times minus 1 divided by 0, and that's not defined. You know, we get minus 1 plus 1 in the denominator. We cannot divide by 0, because 0 times any number gives us 0. We can't multiply 0 by something to give minus 2 on top. If we were to look at the graph of f of x, we would have a break in the graph at x equals minus 1. You see, the function is not defined at minus 1, so the graph will never cross this line. Because if it did cross the line, then the function would have a certain value at minus 1, and that can't happen. This line here has equation x equals minus 1. This equation is got by putting the denominator of the rational function equal to 0. So this line, which represents a boundary for the graph, is referred to as is actually an asymptote. It's a vertical asymptote. See, it's a vertical line. To find the vertical asymptote, we just put the denominator of the function equal to 0. So we just put x plus 1 equal to 0, from which we get x equals minus 1 as the equation of this vertical line. The equation of a vertical line is just x equals a constant. The constant being the value that the line cuts the x-axis at. All points on this line have the property that x equals minus 1. So the equation of a vertical line has a simple form. It's just x equals a constant. Y does not appear in this equation. Another thing about rational functions is that as x approaches a very large positive or negative number, then f of x approaches some value. So for a very large positive value of x, we would see that f of x is approaching a value. Suppose we get f of plus 1000. So plugging 1000 in here, we have 2 times 1000, which is 2000 on top, and we divide by 1000 plus 1. 1000 plus 1 is 1001, of course. You see, we get 1.998. That's the 3 decimal places. So it looks like this number is approaching 2. If we take an even larger value, you would see that that's the case. Suppose we get f of 10,000. So we have 2 times 10,000, which is 20,000. 20,000 is divided by 10,000 plus 1. That's 10,001. See, we get 1.9998. It's even closer to 2. So you can see what's happening. As x tends towards plus infinity, as this number becomes an infinitely large positive number, then f of x is approaching 2. The same is happening for negative values of x. If we take a very large negative number, suppose we take f of minus 1000 and plug it in here, we get 2 times minus 1000, that's minus 2000, divided by minus 1000 plus 1, which is minus 999. This number here is very close to 2. 2000 divided by 999. You see, we get 2.002. And if you imagine taking an even larger negative value, like f of minus 10,000, you'll see that we get a value even closer to 2. So we'll have minus 10,000 times 2 on top. That's minus 20,000 on top. And it's divided by minus 10,000 plus 1, which is minus 900 and it's minus 9,999. You see, we get 2.0002 approximately. See, this number is even closer to 2. So you can see what's happening. As x tends towards plus infinity, for increasingly large positive values of x, our function f of x is approaching 2. These numbers are approaching the number 2. So I'll show 2 on the vertical axis, or the f of x axis. You can also see that as x approaches plus infinity, then our graph is approaching 2 from below. So the curve is approaching this line, but never actually crosses it. You see, for x equals plus 1000, we have 1.998. That's a value that's less than 2. For x equals plus 10,000, we would have a value that's even closer to 2, but less than 2. It's 1.9998. So that's what's happening to the curve here. It's approaching y equals 2 from below. And on the other side, we're approaching y equals 2 from above. So f of minus 1000 is 2.002. It's slightly greater than 2. So we're actually approaching 2 from above for the other section. Now, in general, when you do this question, you won't bother working out these values. We will do it more formally. We'll actually calculate a limit. So what we do to get what's called a horizontal asymptote is we get the limit as x tends towards plus or minus infinity of f of x. So we calculate this limit here. So let's do that now. So we want the limit as x tends towards plus or minus infinity of f of x, which is 2x over x plus 1. Now, in earlier videos, we explained how to calculate limits. You can't just plug infinity directly into this, because you'll have 2 times infinity on top, which is infinity, over infinity plus 1, which is infinity. Infinity divided by infinity is not 1, actually. This limit is not 1. To calculate this limit, we must change the form of our function, so that when we take the limit, we get something meaningful. So what we do is divide above and below by the highest power of x. The highest power of x is 1, so we divide above and below by x. 2x divided by x is 2. X plus 1 divided by x, well, x divided by x is 1, plus, then we have 1 divided by x. So you divide above and below by x. You have to do the same. If you divide above by x, you must divide below by x. So now we get this here. And if we take the limit as x tends towards infinity of the function when it's in this form, we will see that 1 over x will go to 0. As x goes to infinity, whether it's plus infinity or minus infinity, it doesn't matter. 1 over an infinitely large positive or negative number is effectively 0. So we end up at 2 over 1 plus 0. That's 2 divided by 1, which is 2. So we see that the limit is 2, as we saw from plugging numbers in for x. So the equation of the horizontal asymptote is y equals whatever this limit is. So it's y equals 2. The equation of a horizontal line is y equals a constant, and the constant is the value that the line cuts the y-axis at. Now let's draw the sketch of this. We're not asked to do it, but it's useful for answering this question. Well, we already saw that for very large positive values of x, the values of y are approaching 2 from below. And for very large negative values of x, the values of y are approaching 2 from above. We saw that by going to our calculator, plugging in values, but let's suppose you didn't actually do that. Well, what you could do is work out the value of the function at just one point. So at any value of x, I'm going to use 0, it's convenient. So our function is 2x over x plus 1. Let's work it out at 0. So we have 2 times 0 over 0 plus 1. Well, that's just 0 divided by 1, which is 0. So when x is 0, y is 0. So we have the point 0, 0. So 0, 0 is a point on the curve. Now once we know that, we can draw one section of the graph. The two asymptotes cut the plane into 4 regions, and our graph is in 2 of those regions. Well, it's obviously in this quadrant here, because 0, 0 is a point on the graph. And it looks like this. One part is approaching 2 from below, and the other part, the other tail here, is approaching -1, but never actually crosses this line because the function is not defined at x equals -1. Now, once we know that one part of the graph is in this quadrant, we know immediately that the other part must be in this quadrant here. It's just got by reflecting this part through the point of intersection of the two asymptotes. So we just reflect this through this point here. This point here actually has coordinates -1, 2. So you could imagine reflecting, say, this point here, which is 0, 0, through this point and going out the same distance on the other side, and we would have a point on the other section of the graph. The other section actually looks like this. This shape is known as a hyperbola. So both of these sections have exactly the same shape. One section is got from the other section by central symmetry in the point with coordinates -1, 2. So if you like, the point -1, 2 is the center of symmetry for the function. You can actually get any point on this section by reflecting a point on this section under central symmetry through the point -1, 2. Now it's a fact that as x approaches -1 from the right here, then f of x is approaching -infinity. You know, you could pick a number that's slightly greater than -1 and work out the value of the function at that point. So for example, if we worked out the value of the function at -0.999, this is a number that is greater than -1. It's to the right of -1, but very close to -1. F of x is 2x over x plus 1. So f of -0.999 is going to be 2 times -0.999 divided by -0.999 plus 1. That's actually 0.001. If you work this out, you get approximately -2000. You see, you get a large negative value. Okay, so at -0.999 we have a very large negative value. So you can see that the graph is approaching the vertical asymptote x equals -1, but never crossing it. You could imagine taking a number even closer to 1, like this number here, -0.9999, and we will get an even larger negative number, a larger negative number than -2000. We'll actually get a number that's approximately -20,000, and so on. As x approaches -1 from the other side, we have a different situation. If we take numbers that are slightly less than -1, suppose we work out f at -1.001, that's a number to the left of -1, we will get a very large positive result. This would actually give us a value that is approximately +2000. So we get a very large positive number. And as x gets closer and closer to -1, f of x is heading off towards +infinity. In part 2, we are given that P and Q are distinct points on the curve. The tangent at Q is parallel to the tangent at P. The coordinates of P are 1, 1. So 1, 1 must be a point on the curve. If you wanted to verify that 1, 1 is a point on the curve, you could just calculate f of 1. Just plug 1 in for x in this. So we have 2 times 1 over 1 plus 1. That's equal to 2 divided by 2, which is 1. So that shows that 1, 1 is indeed a point on the curve. So we have a tangent to the point P. And we have another tangent to a point Q. And the second tangent is parallel to this tangent. So the second tangent can't be on this section of the graph, because as a matter of fact, for values of x greater than -1, the tangents are actually increasing. Sorry, the function is increasing. So, and the slopes of the tangents are decreasing. at minus 1 you could say the slope of the tangent is infinite. We just have a vertical line at minus 1, although the function isn't really defined at minus 1. We could say in the limit at x equals minus 1 we have a vertical tangent, and for increasing values of x, the slopes of the tangents are decreasing, leveling off to 0, so that at x equals plus infinity the slope of the tangent is 0. We have a horizontal tangent. So all the tangents have different slopes on this section. So Q must be a point on this curve here. So the tangent at Q is parallel to this line here. The question that we have here is to find the coordinates of this point Q. So we're going to consider the x value of the point Q. Now one way to do it would be just to reflect the point 1, 1 through the point minus 1, 2. That's the easiest way to do it actually. That's turns out this way will actually give us the correct answer. But I'm not going to do it that way, because in part 3 we have to verify that the point minus 1, 2, that's the point of intersection of the asymptotes, is the midpoint of the line joining P and Q. So I'm going to just assume that we don't know that this point here is the midpoint of P and Q. So how would we find the coordinates of point Q? Well, we see that the slopes of the two tangents are the same. What's the slope of this tangent here? Well, the slope of a tangent is the derivative of the function f prime, but here it's worked out at x equals 1. So it's f prime at 1. So let's get f prime of x, and then we can get f prime at 1. So we'll have the slope of this tangent, and we'll know that it's equal to the slope of this tangent as well. And knowing the slope of this tangent, we can then work out the coordinates of point Q. So we need to differentiate this function here. This function is a quotient. It's got the form u over v, so we use the quotient rule. So the quotient rule is v du dx, x plus 1 times the derivative of 2x, which is 2, minus u, which is 2x, times dv dx, which is 1, and the whole lot is divided by v squared. That's x plus 1 squared. So multiplying 2 into x plus 1 here, we get a plus 2x, which will cancel with this minus 2x over here. And then we have 2 times 1 on top, which is 2. So we have 2 over x plus 1 squared. So now we want the derivative at x equals 1. So we just plug 1 into this. We get 2 over 1 plus 1 squared. Well, 1 plus 1 is 2, 2 squared is 4. 2 over 4, which is a half. So now we know that the slope of the tangents is a half. So, in particular, the slope of this tangent is a half. But the slope of this tangent is the derivative of the function at x. I'm saying that x is the x value of q. So by solving the equation f prime of x equals a half, we can find out the x value of q. So here is f prime of x. We put it equal to a half and we solve to find x. We have a single fraction on each side of this equation, so we can just cross multiply. X plus 1 squared equals 4. To get x plus 1, the easiest thing to do is just get the square root of 4. The square root of 4 is either plus 2 or minus 2. That's the easiest way to solve this equation. You don't have to expand this out and get it into the standard form of a quadratic equation. Just get the square root of 4, and that leads to two linear equations. We either have x plus 1 equals plus 2, or we have x plus 1 equals minus 2, depending on whether we take the negative or the positive or negative square root of 4. If x plus 1 equals plus 2, we get x equals 2 minus 1, which is 1. If x plus 1 equals minus 2, we get x equals minus 3. So here are our two solutions. We already have one of the solutions, x equals 1. We know that f prime at 1 is a half. But we found a new one now, x equals minus 3. So it must be this one here, of course. So the x value of q is minus 3. How do we find the y value of q? Well, q is a point that's on the curve. So the point q has to satisfy the equation of the curve. Well, we know that the equation of the curve is 2x over x plus 1. So we want to find f of minus 3. So we plug minus 3 in here. So we have 2 times minus 3 is minus 6 over minus 3 plus 1. That's minus 2. This works out to be plus 3. Verify that the point of intersection of the asymptotes is the midpoint of PQ. So here's the point of intersection of the asymptotes. X is minus 1 because the point is on the line x equals minus 1. Y equals 2 because this point is on the line y equals 2. So we want to get the midpoint of P and Q. Well, to get the midpoint of 2 points, all we do is get the mean of the x values and the mean of the y values. So the midpoint is 1 plus minus 3 over 2. That's the midpoint of the x values. The midpoint of the y values is 1 plus 3 over 2. So that's going to be minus 2 over 2, which is minus 1, and 4 over 2, which is 2. So we can see indeed that minus 1, 2 is the midpoint of P and Q. So that's true in general. If we have one section of the curve and the intersection of the asymptotes, we can get the other section by just mapping all the points on this section of the curve through the intersection of the two asymptotes. And we can graph the other section that way. We can also show that this point is the midpoint by just drawing in two congruent triangles. The base of this triangle is 2 units long. We just count the squares. We're going from plus 1 to minus 1. The base of this triangle here is also 2 units. The vertical side of it, this triangle here, well, we're going from 1 up to 2. The vertical side is 1, and the vertical side of this one is also 1. That's from going from 2 up to 3. We have two congruent triangles, so everything about them is the same.